Okay, I present Multihop Cooperative Perception with Mitigating Sidelink Resource Breaks by Packet Filtering. The presenter is Masashi Kunibe at the Department of Information and Computer Science of Keio University. Here is today's agenda. In cooperative perception, vehicles share in-vehicle sensor data through wireless communication. As a result, they can extend perceptible range on roads. Figure 1 shows the example of cooperative perception. As shown in Figure 1, the connected and autonomous vehicle 2 sends the information of vehicle 1 to cave 1. As a result, cave 1 can recognize vehicle 1 even if vehicle 1 is hidden by cave 2. The challenging task of the cooperative perception is that vehicles send the cooperative perception information in specific range by the reliable vehicle-to-everything communication. Here is the overview of the V2X communication architecture. The architecture is composed of facility layer, network layer, and access layer. In the facility layer, vehicles generate messages such as cooperative awareness message, that is called COM, and cooperative perception message, that is called CPM. The COM includes speed, position, and heading of vehicles, and CPM includes speed, position, and perceived objects by in-vehicle sensors. Especially the ETSI standard generates COMs and CPMs periodically. The generated message goes to the network layer, and the network layer sends messages in specific range by multi-hopping. There are two technologies such as greedy forwarding and contention-based forwarding. In GF, the packet sender selects the next word, and in CPF, the packet receiver determines whether to become the next word. And in general, CPF is robust to the packet loss rather than GF. In access layer, the vehicles select the best wireless resources in the single hop, and there are two technologies such as DSLC and Celebrity-X. In DSLC, vehicles listen the wireless resources every transmission, and in Celebrity-X, vehicles resolve wireless resources periodically. In this research, we introduced CPF to Celebrity-X for sending messages in specific range. Here is the explanation of CPF. In CPF, receiver vehicles wait to forward the packet for TO-CPF GUC seconds, and TO-CPF GUC is determined by the distance between sender and receiver. Figure 2 shows the example of TO-CPF GUC calculation. As shown in Figure 2, the sender sends a packet and the two receiver receives the packet. And the TO-CPF GUC is calculated as shown in the graph. As shown in the graph, the TO-CPF GUC decreases as the distance between sender and receiver increases. So, the receiver with the long distance from the sender becomes the next word. And then the packet lifetime decreases by TO-CPF GUC seconds. In access layer, vehicles resolve Sidelink resources with fixed interval and subchannels. Especially, vehicle-to-vehicle communication in Celebrity-X is named as Sidelink communication. And Figure 3 shows the Sidelink resource reservation. As shown in Figure 3, the new resources are selected from candidate single subframe resources, that is named CSLs, and then the 80% CSLs with the highest RSSI are filtered from all the CSLs. And the CSRs are determined by Sidelink control information, and Sidelink control information includes the used subchannels and resource reservation interval. By concealing the used subchannels and resource reservation interval, the vehicle can mitigate the packet collision. On the other hand, the multi-hop communication tends to generate the aperiodic traffic. As a result, the aperiodic packet traffic breaks the reserved resources in Celebrity-X. Figure 4 shows the reasons for breaking reserved resources. The first case is that there are no packets at the transmission time, and the second case is that there are no enough reserved resources within the packet lifetime, and the third case is that there are no enough reserved resources compared with the required resource size. In single hop communication, the first case is caused by the periodic packet generation because the packet generation intervals is periodic. In addition to the first case, in the multi-hop communication, the second and third cases are also occurred because in the network layer, the packet lifetime decreases, and the network layer generates irregular amount of packets. By these reasons, vehicles have to reserve new resources frequently, and packet collisions are occurred frequently by selecting the same resources among different vehicles. Therefore, we have to mitigate the influence of these reasons on the reliable multi-hop communication. So, in the proposed method, the method filters and discards the packets that break the reserved resources. Figure 5 shows the proposed procedures. First, I'll explain the normal procedure, and after that, I'll explain the proposed procedures. A normal procedure, vehicle generates messages or packet in the facility layer, and the packets goes to the access layer. And if the vehicle needs new resources, vehicle calculates shear salts and wait the transmission time. At the transmission time, vehicle generate MAC-PDU by the packets and send the MAC-PDU. When vehicle receives the MAC-PDU, the vehicles get the packets from the MAC-PDU, and the packets goes to the network layer. And packet encode into the CBF queue and wait for TO-CBF GUC seconds. After TO-CBF GUC seconds, the vehicle dequeued packets and the packets goes to the access layer. And then the network layer generates a regular amount of packets and the packet lifetime decreases. Therefore, these packets breaks the reserved resources in access layer. So, the proposed method filters and discards the packet that break the reserved resources. On the other hand, the filtering may degrade the perception quality. So, the proposed method fetches the packets from CBF queue if there is enough resource. This is the explanation of filtering packet. The method seeks tentative transmission time for sending packets, and the method filters the packet if the tentative transmission time is earlier than the current transmission time. Figure 6 shows the example of tentative transmission time calculation. Subfig A is the current reserved resources, and subfig B is the tentative resource calculation. In subfig A, vehicle can utilize 4 subchannels for sending the packet, and in subfig B, vehicle can utilize 6 subchannels for sending the packet. So, if the vehicle needs more subchannels rather than 4 subchannels, the vehicle may set the earlier transmission time rather than current transmission time. Then the packet breaks the reserved resources, so the proposed method filters the packet. On the other hand, the packet filtering may degrade the perception quality. So, the proposed method fetches the packets from the network layer if there is enough room in resources. Figure 7 shows the example of fetching packet. Figure 7 shows the example of fetching packets from the network layer. As shown in Figure 7, vehicles send packet N, and there is remaining resources in blue color. Then the vehicle fetches packet such that the packet size is within the remaining size. By fetching packet, vehicle can utilize the reserved resources efficiently, and the perception quality is kept. In the simulation, we utilize Sumo color, and OpenCP2X as mobility and vehicle sensors and wireless communication simulators. Figure 8 shows the simulation architecture. We simulate vehicle mobility in color, in Simo, and vehicles perceive each other by their in-vehicle sensors. The in-vehicle sensors is introduced by color, and the sensor data is logged. And the logged sensor data is loaded into the OpenCP2X, and in the OpenCP2X, we could generate CPMs and comms based on the sensor data. Here is the simulation parameter. The road length is 2 km and the width is 3.2 meter. The number of vehicles is 139 to 144. The simulation duration is 20 seconds. The sensor type is radar and the sensor range is 150 meters. The horizontal half is 360 degrees. The vehicles generate messages by the H standard, and the command size is 300 byte, and the maximum CPM size is 450 byte. The CPM size changes by the perceived object. The details is listed in the table 2. Here is the simulation parameters of access layer. We utilize 5 subchannels, and the transmission time is 23 dBm. The vehicle selects 150 and 20 milliseconds as the possible RRIs. The carrier frequency is 5.9 GHz. We utilize 2 evaluation metrics, such as perception ratio and packet delivery ratio. The packet ratio is defined that the ratio of the number of perceived vehicles to the number of all vehicles in the distance. And packet delivery ratio is defined that the ratio of the number of received packets to the number of sent packets at the distance. Figure 10 shows the evaluation of perception ratio to the distance. The line is the perception quality of CPM, and the dashed line is the perception quality of COM. When vehicles send the message in the single hop communication that is colored in yellow, the vehicle can perceive within the 400 meter by the COM and about 600 meter by CPM. And when vehicle utilize the two-hop communication and the maximum TiVo CVF is 100 milliseconds, the perception quality of the two-hop communication and single-hop communication is almost the same. This result indicates that the network layer duration, such as TOCP FGOC, is long for the packet transmission. That means that the packets are discarded in the network layer due to the TOCP FGOC seconds. Therefore, we set the short TOCPF max second as 10 millisecond. That is red and blue. Especially the red color means the proposed method, and the blue color means the case without the proposed method. As shown in figure 10, the red color, that means the proposed method, extend the perception quality. On the other hand, without the proposed method, the perception ratio of the COM is the lowest. This result indicates that the proposed method mitigates the influence of the resource breaking in the access layer on the perception ratio. On the other hand, or in the other words, without the proposed method, the multi-hop communication frequently breaks the resolved resources and the perception quality also decreases. The figure 11 is the packet delivery ratio to the distance. The yellow line is the single hop communication, and the green line is the two hop communication, with the TOCBF max is 100 millisecond. The red color is the second hop communication, and the TOCBF max is 10 millisecond. The blue color is the case without the proposed method. As shown in figure 11, the method with multi-hop communication decreases, PDR. This is because the multi-hop communication, in the multi-hop communication, there are too many packets compared with the single-hop communication. On the other hand, the proposed method improves the PDR compared with the case without the proposed method. This result indicates that the proposed method can mitigate the Sidelink resource breaking. Here is the conclusion. In cooperative perception, we could share cooperative perception information to extend the perceptible range on rows. And the challenging task is that the information should be spread into the specific range by the reliable vehicle-to-everything communication. The multi-hop communication can spread message in the specific range. On the other hand, the multi-hop communication easily breaks the Sidelink resources. So, the proposed method filters and discards the packets that will break the reserved Sidelink resources. Furthermore, to mitigate the degradation of the perception quality, the method fetches packets from the network layer if there is enough room in the reserved resources. In the evaluation, we introduced the proposed method into the Syllable-to-X architecture that is composed Etsy message generation, and CBF, and Syllable-to-X Sidelink reservation. And the proposed method improves the perception quality and PDR compared with the case without the proposed method. And that is the list of references. Thank you for listening.